Hello, mathematicians. Today we're going to be learning about scientific notation. And scientific notation is a way for us to represent very large or very small numbers. So we're going to go through some examples first of scientific notation and see if we could find any patterns. So here I have 5 multiplied by different powers of 10. These are all representations of scientific notation that I'm now going to change into standard form. And by doing so, I'm going to rewrite 5 times 10 to the power of 0 is 1. Remember that any number that's not 0 to the power of 0 is always equal to 1. So 5 times 1 is equal to 5. 5 times 10 to the power 1 is 5 times 10, which is equal to 50. 5 times 10 to the power of 2 is 5 times 100, which is equal to 500. 5 times 10 to the power of 3 is 5 times 1,000, which is equal to 5,000. 5 times 10 to the power of 4 is 5 times 10,000, which equals to 50,000. And 5 times 10 to the power of 5 is 100,000, which equals 500,000. So take a look and see if you see any patterns. So here, when we multiplied times 10 to the power of 0, notice that our number did not change. So it's the same thing as 5 times 1 because it is 5 times 1. Here, I have 5 times 10 to the power of 1. Notice now that I have 1 0. Here I have 5 times 10 to the power of 2. Notice here that I have 2 zeros. 5 times 10 to the power of 3. Notice that I have 3 zeros, and so on. Now, even though this pattern is here, it's not always about the zeros, and I'll show you guys that in a later slide. But just see how our place value changes depending on what power of 10 we multiply 5 by. So, working with a calculator. So whenever I take a calculator and let's say I multiply 5 times 10 to the power of, let's say, 16. That means I'm going to take 5 and multiply it by 10 16 times. So I'm going to actually use my scientific calculator to write out 10 to the power of 16 first, because that's a large number, times 5. And now notice that there's an E here. And depending on which calculator you use, it's either going to be a capital or a lowercase e. Usually I find that it's an uppercase E, and basically 5e16 is the same thing as 5 times 10 to the power of 16. And the reason why our calculator shows E is because there's too many digits to represent our answer. However, based on our previous pattern, we know that it would be 5 with 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Okay? And that's how we would represent 5 times 10 to the power 16. And based on this, you could see why we write it in scientific notation, because this is a very large number, and it's a lot easier to write it in scientific notation and look at it in scientific notation than it is in standard form. So here I have negative exponents, and we're going to go over what that means. So 5 times 10 to the power of 0 is 5 times 1, as we did before, which is equal to 5. And here, remember that 10 to the power of negative 1 is the same thing as 1 over 10 to the power of 1, which is basically a tenth, if that makes it easier for you. So it's 5 times, either we could do the fraction or the decimal. So 5 times a tenth, which is 0.5. And then next we have 10 to the power of negative 2, which equals 1 over 10 to the power of 2, which is 1 over 100, which equals 0.01. So it's 5 times 100th, okay, which is 0.05, which is 5 hundredths. And then if you notice, a pattern starts happening here. So it's going to be 5 times 1,000th. So I get 5,000th, and so on. Okay, so there also is a pattern here. Instead of making our number larger, the lower the exponent, the smaller our number is. So again, working with the calculator, if I had 5 times 10 to the power of negative 16, I'm going to type in 10 to the power of 10 to the power of 16, negative 16, times 5, and you'll notice that the same thing happens. So these two are equivalent. And the way we would do that is we have 5, and we're going to go back 16 times. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Add my decimal and add a 0. And as you could see, we write that in scientific notation because this is very difficult to write out and very difficult to work with. So here, I just have a short summary for you guys. If we're multiplying by a positive power of 10, so 10 to the 4th power, we move the decimal to the right. So we start here after the 7 and we move it once. So 1, 2, 3, 4, and then our decimal moves to the back, making it 70,000. And if we're working with a negative power of 10, we start after the 7, so that's where my decimal place is at. And we're going to move to the left 4, so 1, 2, 3, 4. And that's why it ends up there. And we end up with 0.0007. So when we're working with scientific notation, it's very important that the number we're working with, the one starting off, is between 1 and 9. So for example, even though I could write 70 times 10 to the power of 3, and that would be 70, and then I'd move the decimal over 1, 2, 3, and get the same number. This is not how scientific notation is written. So to make it easier in scientific notation to compare numbers, we always make sure that the first leading value is between 1 and 9, so that we could easily use our exponents to compare how big and how small numbers are. So here we have two problems, and we're going to convert from standard form to scientific notation. So the first one says the length of a sugar grain is about 7/100 of a centimeter to 14/100 of a centimeter. So we're going to start off with 7/100, and because it's a decimal and we want the leading number to be between 1 and 9, we're going to have a negative exponent because now we're going to rewrite it in scientific notation, but the standard form is a decimal. And I'm going to show you guys what that means. So here we know that our decimal has to be after the 7. So 7 times 10 to the power of. So if we're going to have 7 and we want to go back to our initial value, our decimal is going to be here. And in order to get 7/100, we have to move the decimal back to the left. So times 10 to the power of -2, because we want to come back to standard form, but we just want to rewrite it in scientific notation. So because our decimal goes to the left from the end of 7, it's 10 to the power of -2. Okay, and we could always check that by writing 7 decimals here. We go to the left 2. We end up with the same amount. And now our second value, this one's a little bit different. Now here, if we moved our decimal over, if our decimal was in between the 1 and the 4, 1 and 4/10 is between 1 and 9. We don't want to move it over more because if we did, our leading value would be 14, which is not between 1 and 10. So it's going to be 1 and 4/10 times 10 to the power of -1, because even though we're moving our decimal to the right, if we want to return back to standard form, we would have to take this decimal and move it to the left. All right, so the next problem says particles of sand range from 5/1000 of a centimeter to 2/10 of a centimeter. So taking our first value, we know that the leading number in our scientific notation has to be between 1 and 9. So our decimal would have to be here. And if we want to go back to standard form, we're moving to the left. So 1, 2, 3. So it's going to be 5 times 10 to the -3rd power. And looking at our second value, we have 2/10. And our decimal would have to go to the right of 2. But if we want to go back to standard form, it would have to go to the left one, making this 2 times 10 to the power of -1. And the reason why we have that leading number between 1 and 9 is because if we look at these two up here, 10 to the power of -2 and 10 to the power of -1, we know that -2 is smaller than -1, and if we were just looking at these two in scientific notation, we could see that 7 to the power times 10 to the power of -2 is smaller because -2 is smaller. Here, -3 is smaller, so by looking at these two values in scientific notation, -3 is smaller, so that number is smaller in scientific notation, okay? So the two that I have underlined are smaller because their exponent is smaller and they're both written in scientific notation correctly. So here we have convert from scientific notation to standard form. And now I have everything in scientific notation, and we're going to change it to standard form. So the thickness of paper is between 5 times 10 to the -3rd power centimeters to 1 times 10 to the -2 centimeters. And we're going to write that out again. Well, actually, we don't have to. So here, if we write out 5, because this is -3, we start with our decimal. And since it's negative, we're going to move to the left 3. So 1, 2, 3. Decimal goes here. 0, 0, 0. So we have 5 thousandths. And then here I'm going to write 1. Because it's negative, I'm moving to the left 2. 1, 2. So I have 1/100 of a centimeter. So the thickness of a paper is between 5 thousandths of a centimeter and 1/100 of a centimeter. So the length of a water molecule is 1.11 times 10 to the -8th power. So I'm going to write our leading value, and because it's 10 to the -8th power, I'm going to move my decimal to the left 8 times. 1, 2, 3, 4, 5, 6, 7, 8. And I'm just going to rewrite this so it's easier to look at. Okay, and as you can see, especially for this last one, why it's easier for some large or very small numbers to write in scientific notation. Again, we're going to convert from standard form to scientific notation. So here we have Mercury has a diameter of about 3,031 and 9/10 of a mile. So I'm going to start off by writing our number again. And we want to make sure again that our leading number is between 1 and 9. So here, in order for this to be in scientific notation, our decimal would have to be between the 3 and the 0. So it would be 3.0319. And in order to get this number back, we would have to move to the right. So 1, 2, 3 to the right. And if we're not sure, we could always go back and check. So because that's 10 to the power of 3, I'd go 1, 2, 3. That is where my decimal started, so it's all good. All right, so the next one says the sun has a diameter of about 864,340 miles. So the first thing I'm going to do is write out our number. And our decimal goes here, and we would like for it to be between the 8 and the 6. So it's 8.6434. In some cases, we would just round this to 8.64 and then times 10 to the power of 1, 2, 3, 4, 5. Okay, and we could always go back and check it if we have to. And then lastly, we're going to convert again from scientific notation to standard form. So Earth has a diameter of about 7.9175 times 10 to the power of 3. First thing I'm going to do is write out our number. And then since it's to the power of 3, I'm going to move the decimal over 3 times. 1, 2, 3. And I have 7,917 and 5/10. And this should be miles. And then Finally, Uranus has a diameter of about 3.1518 times 10 to the power 4. And we're going to move the decimal 4 times to the right. So that's 31,518 miles.